So the last video for this lesson is about the modulo operator. Well, mostly about the modulo operator and a little bit about integer division operator. A formal mathematical definition of the modulo is given in the Jupyter notebook, but we will use the idea that it's just a simple remainder. So when I do a modulo operation, the number that comes out is what the remainder of that division would have been. So it's basically throwing away how many times it goes in and just thinking about what the remainder is. Our first example that that I'm going to talk about right now is one that you'll encounter many times during this course. Taking a vector of numbers and turning it into a matrix of numbers with a set number of columns is something that you're going to have to be able to do. And just realize that the number of columns and rows must make sense. In other words, here you can see that I have 12 numbers and I want to turn it into a matrix of the 3 by 4. So the 3 times 4 must equal 12. I mean, in other words, if I was trying to get 5 columns out of this, it wouldn't make sense because I would have 1 through 5 and then 6 through 10, and then I had 2 extra numbers left over, and so that wouldn't make a whole lot of sense. But I can certainly do 6 columns with 2 rows, or I could do 2 columns with 6 rows, or 3 and 4, or 4 and 3. I mean, so you'll see this problem in the future. So let's go ahead and sort of try to figure out what we're trying to do, or how we would go about doing this. And so what I'm trying to do is break this thing up into basically 3 groups. I'm going to call this group 1, this one 2, and this one 3. And how can we go about doing that? So what I want to do is use the number. So these numbers could be anything in here, but I could certainly get the index out of this vector, right? So this vector could be negative 27 in the one spot. So this could be negative 27. This could be 30, 57, 42. I'm not really concerned with that, but what I am is the index, right? So I could always get the index. This is index 1 of that vector, index 2 of that vector, index 3 of that vector. So that's why I wrote basically numbers through 1 through 12, because those represent the index. And then what we want to do is we want to map this over to the matrix, where this right here would be the row 1, column 1, and this would be row 1, column 2, and 1, 3, and so on and so forth, right? So this one would be, for example, just kind of going in here, 2, comma 2, right? So it would be row 2, column 2, row 2, column 3, row 2, column 4, and so on and so forth, right? So this last one would be 3, comma 4. So is there a way to map that number 12 to the number 3, comma 4? Is there a way to map 11 to 3, comma 3, comma 3? Right, because that would be the 3rd row and the 3rd column. Okay, so that's the idea. Can we do that? Let me try to erase that. Okay. And how would we go about doing that? So the first one is, well, can I take the numbers 1 through 4 and map it to 1? Let's see here. What if I did integer division? So 1 integer to divide the number of columns. So I claim that the number of columns is the important number here. So 1 div 4, 2 div 4, 3 div 4, and 4 div 4. Well, what does that come out to be? Well, that would be a 0. This would be a 0. This would be a 0, and then this would be a 1. So we've almost done what we want to do. Okay, so how could I go about and changing it so that these 3 are still mapped to 0, but this one also goes to 0? Well, I claim that what if you did this? What if you took whatever the index is, 1, and subtracted 1, and then div 4, and then we would get 0, and then 2 minus 1. So I'm subtracting 1 from each one of these, and then divide, and then doing the integer division. So that would be 4, and so on and so forth, all the way till we get the 4 minus 1 div 4 would also be 0. So those numbers would give us 0. And then what would we need to do to the 0 in order to map it to the 1, because that's really what we're concerned with? Well, we would just add 1 to all of these. So if I'm going to write code for this, I would say take the index, the IDX, the index, subtract 1, integer divide by 4, and then add 1 to it. And that would map this index to the row. So let's just make sure that it works for the second row. Hopefully it does, but let's just make sure. So with this 5 minus 1 div 4, right? 5 minus, so that's 1 plus 1. Does that go to 2? And the answer is yes. How about 6 minus 1? Oops, I don't need a parenthesis there. I guess I do. This needs to be a parenthesis. And then div 4. And then you don't necessarily need a parenthesis there. And then plus 1. So 6 minus 1 is 5. 5 div 4 gives us a 1 in the divisor. And then plus 1, so that gives us 2. And then, and so on and so forth, right? So what about 9? 9 minus 1 is 8. 8 div 4 plus 1. So that's 2 plus 1 would give us 3. So it looks like it's working. And we'll implement it in code here in a few minutes in order to make sure that it does what we suspect it would do. But since we haven't used our modulo operator, you're probably thinking that maybe we might need to do something with a modulo, and that's true. In this next part, what I want to find is I want this to be a 1, this to be a 2, this to be a 3, this to be a 4, and then I want this to be a 1, a 2, a 3, a 4, a 1, a 2, a 3, a 4. And why is that? Because these numbers in red line up with the columns that each one of these. So 1, 5, and 9 should each have 1 associated with it, and 2, 6, and 10 should each have a 2 associated with them, and so on and so forth, right? So you can kind of see the 2, 6, and the 10 coming from the numbers underneath, the little red numbers underneath. So how would we do that? Well, let's just start off with the same idea. Let's go IDX, and then we'll check it. IDX minus 1 modulo number of columns. Modulo. So this is div columns, right? So I probably should have used number of columns here instead of. So if you want to generalize these things, you should absolutely use the general case. So if I change that to 6, then it should also work. In this case, I'm gonna check this to see if it works. So let's see if 1 maps to 1. So IDX minus 1. So 1 minus 1. Oh, we forgot to add our 1. So don't forget that piece needs to be in there as well. So 1 minus 1 modulo 4 plus 1. So that's 0 modulo 4. So this ends up being 1, which is what we want it to be. And then what happens when I put a 2 in? 2 minus 1 modulo 4. So 2 minus 1 is 1. Modulo 4 gives us 1. 1 plus 1 is 2. And then you can, as you can imagine, this rest of this all the way up until the modulo 4 actually becomes into play. Plus 1, plus 1. All right, let's see what happens at 4. No, let's see what happens at 5, because 5 is when the modulo actually comes into play here. So 5 minus 1 gives us 4. 4 modulo 4 is 0, then plus 1. So that would be 1. So 5 maps to 1. Is that what we want it to do? Yes, it is, because we want that to be row 2, column 1. All right, so it looks like this is our formula for mapping these numbers to the column. So this would be column. And this looks like this, so I'll rewrite it in blue and use the general case. So IDX minus 1, integer division, number of columns, plus 1. Gives us the row. All right, let's just see how that works out when we pull it up in Python. And so the cool thing over here, console restart, we'll restart the kernel. I like restarting the kernel to get us kind of where, so I've already put in the math, right? So this is an F string. And if you look over here, you see IDX minus 1 divided by, or integer division in C, right? I could have put a parenthesis, but because the order of operations, we know that'll work, and then I'll add the 1 to it. Same thing here, IDX minus 1, integer division number of columns plus 1. So if I put 4 in here, I expect, so for position 1, we get 1, 1. For position 2, we get 1, 2, 1, 3, 1, 4. And that, I think that's what we wanted it to be over in. Let me grab this, put it to the side, and then put there it is. Okay. So it was, it's over. 5 was 2, 1. 6 was 2, 2. 7 was 2, 3. 8 was 2, 4. And we see that it's doing what we expect it to do. And so the neat thing is, if you're good about how you program, then you can come up and you can change this to a 6 and then redo it. So then it would give you row 1 all the way through 6, and then row 2 all the way to 6 for each one of those individual pieces. All right, that is stacking data, so a row of data into a matrix or a column of data into a matrix. Let's now talk about a linear congruential random number generator. That's also using the modulo operator. So we will eventually need the computer. If we want to solve stochastic type problems, we will need the computer to produce random numbers. And the problem is there's not, and there's 3 things that we really want it to do. We want it to be fast, we want it to be repeatable, and we want them to be random. The problem is if it's fast and repeatable, it's probably, I don't even know if you, well, I haven't studied it, so I don't know really if you can do repeatable ones that are truly random. But so what we do instead of this is we really concentrate on the fast, because you're going to need a whole lot of random numbers to do some of these simulations. And the fact that we want it to be repeatable means that we want to reproduce the results if we're interested in it. So what we end up doing is using this thing called a linear congruential random number generator. So let me pull up our OneNote here, and then we get, so this ends up being the equation that we use. So, and what it is just you could think of it, it's not really a discrete dynamical system, but because I'm thinking about the modulo operator, but it is certainly a sequence, right? So this is a sequence of numbers, and what it's doing is it's got some number here. So you're taking whatever A is, whatever you decide for A to be, and you're taking the previous number. For example, let's just suppose that we start off at 0. So 0 times A plus C, and then modulo whatever your M is. And we want M to be a very large number, and then we want to get the full period, what's called a period of M. So for the number below, so we're going to use this theorem, and we'll use it over here in a more difficult problem, but we're going to use this theorem to ensure that we get a maximum period for whatever our M is. And in this case, I just chose M equals 5, so we can just see sort of what happens. In this case, you'll see here in a second, actually, you can see it right here. So if M equals 5, then we want to choose C so that it's relatively prime to M. So that just means choose any C that doesn't have a 5 in it. So I can't choose 10, I can't choose 15, I can't choose 20. You'll see over here that it's a combination of those 2 prime numbers that we don't want to choose a C. Yeah, C got to be some other number besides a combination of those other 2 numbers. But in this case, C equals 7, C could equal 4, C could equal 3. I mean, there's lots of things that C could be equal to as long as it's not as long as it's relatively prime to M. And then this next line says A minus 1 is a multiple of P for every prime dividing M. And so 5 is the only prime. So so I should have probably wrote A minus 1 is equal to 5 times some integer value Q. Because if I can find an integer value Q that fits this equation, then we can find out what an A is. For example, in this case, if we just use Q equals 1, 1 times 5 plus 1 is equal to 6. And so this is the only equation that we have to worry about to satisfy. As long as I choose an integer Q that in 1, 2, 3, any of those will work, and we'll see that A will produce a full period of 5. Okay, so in this case, I just chose Q is equal to 1, A is equal to 6, and so I have my A, my C, and my M, and realize that this is certainly not a really good M, right? Because we don't want the computer to produce 5 numbers. I mean, that's the largest period you could think of. You're going to have a 0, a 1, a 2, a 3, and a 4, and those are the only things it could be. Anything divided by 5 is going to be some number between 0 and 4, 0, 1, 2, 3, or 4. So that would be the largest period that we would have, but we just are showing this for demonstration purposes, right? So I could actually just do the math myself. Okay, so suppose we start off with our seed, right? Because this is called the seed, the first number in your sequence, x0. You may have heard that before when you're talking about random numbers in the computer. So seed it at 0, and then find out what happens. Well, then take 6, because 6 was A, so it's A times xi, which x0 or 0. 6 times 0 plus 7 is 7. 7 mod 5 gives me a remainder of 2, and that's where the 2 comes from, and the 2 gets substituted into here. 6 times 2 is 12. 12 plus 7 is 19. 19 mod 5. Modulo 5 is 4, because there's 4. 3 times 5 would be 15. 19 minus 15 would be 4. And then take that 4, put it in. 24, 31. Because that's 24 plus 7 would be 31. 31 mod 5 gives you 1. And then take that 1, put it in. 1 times 6 plus 7 is 13. Gives you 3. 3 goes in here. So this person, these folks, Hull and Boble, came up with this theorem here. So in order to get a period of M, these things have to be satisfied, and we'll see here in a few minutes. I'm going to change the A and the C here. We're going to leave M as 5, and you're going to see that this period is not going to work out for us to our favor. Okay, so with that being said, let's go over and look at a more difficult one. So I'm going to find A and C when M is equal to 100 now, using the same theorem, using the same ideas. So the first step is to find the primes of M. So M's 100, and then I'm sure everyone's seen this before. You just kind of multiply it out until you get all of the factors here at the bottom, and then put the factors together, and you see that 2 and 5 are your 2 primes. And then choose C, so that's relatively prime with M. Choose any number that does not have a 2 and a 5 as a multiple. For example, 7. Right? 7 times 3 is 21. So 7 and 3 is not a 2 or a 5. 3 times 3, 9. That's another one. 7 times 7 is 49. That's another one. I mean, there's lots of choices here for C. Some of them are good, some of them are bad, but we won't necessarily care about that. All we care about right now, anyway, is getting the full period of 100. Obviously, you can't choose 8. Why? Because 2 is a multiple of it. You can't choose 15 because 5 is a multiple of it. So you got to choose any of them that sort of has no multiple of the prime numbers that came out of the 100. And then finally is sort of the hardest part of this, right? So using these last 2 things here, A minus 1 is a multiple of P for every prime. So I have 2 primes now. I have 2 and 5. And so that's where these first two equations come from. Let's see. Yeah, I can use blue. So these come from number 2, and this one comes from number 3, because 100 is in fact a multiple of 4, right? So 4. So 100 is a multiple of 4. So we have to worry about this last one. So that's where this last one comes from. And then you just take this. So the problem is they have to be multiples, so these must be integer values, right? So I got to choose P, Q, and R that satisfy these, and all of them are integers. So we come down here, and I just rewrote. All I did was I took the 1 to the other side, so A is equal to 2P plus 1. A also needs to be equal to 5Q plus 1, and A must also equal to 4R plus 1. So these must be satisfied. And so let's just throw in a couple numbers. I think I'm going to start with Q. I mean, it's your choice on which one you start. The problem is if I usually use the biggest one. So in this case, Q is equal to 1. Can we solve for the other 2? So if Q is equal to 1, then that means A is equal to 6. And the question is, do these other 2 solve? So 6 minus 1 is 5, and that will not solve. So 2, is not equal to 2p plus 1. You can't get an integer out of that when a is equal to 6. So we're not going to worry about that one. So q is equal to 1 is out of the question, or out of the ballpark there. So let's try q is equal to 2. Q is equal to 2 gives us 11. So a is equal to 11. And the question is, can we solve these other two, right? Is there a p, an integer p that I can substitute in? Let's see, 1, 10. So there it is. So p would equal 5. All right, so a equal 11 held up for that first one. And then 4 minus, so 4r equals 10 minus 1 is 11. So 11 minus 1 is 10, so 10. So that one goes away too. So that one doesn't work either. How about q is equal to 3? Believe it or not, there's probably some pretty easy code. So there's some easy code that we could come up with to do this. But we're doing it by hand, that's fine. Because it's not going to go too much further. So this would be q times 15 plus 1 is 16. So 16 won't work because it's an even number. I know right now that needs to have an odd number in it. So q is equal to 4. Q is equal to 4 is 21. So a is equal to 21. And if that's equal to 21, then p must be equal to 10. And does it solve for r2? There you go. R is equal to 5, because 5 times 4 gives you, so 5 times 4 gives you 20. 20 plus 1 is 21, so it solves. There we go. And so a is equal to 21 is what we're going to solve or use. We will use c is equal to, it doesn't really matter here, one of these ones. C is equal to 7, and then m is equal to 100. And what we want is to have a full period. A full period means equal to 100. All right, so let's take this and stack it up over here and find our spider in Python. So I'm going to move that over a little bit. And what I've done is I've written a little bit of code here that will do it for us, right? So it'll print it off over here for us. And so just make sure that we're doing what I said we were going to do. So m is equal to 5, a is equal to 6, c is equal to 7. Let's find out what the period is of that one. F9. You can see it gets the same, hopefully it gets the same numbers we came up with, right? So 1's equal to 2, the second one's equal to 4, third one's equal to 1, fourth one's equal to 3, and the fifth one's equal to 0. Let's find out what happens if I didn't choose a is equal to 6. Let's find out what happens when a is equal to 1. Oh, a equals 1 works too, because q is equal to 0. All right, how about something different, something that won't work? All right, so the period on when a is equal to 2 is only 4, right? So you only get 4 of the numbers. So we're missing 0, 1, 2. We're missing 3. So 3 is not in there. You can see that doesn't work. 3. Let's find out what that one is. Also equal to 4, and you're missing 0, 1, 2, 3. You're missing 4 this time. Let's see. You only get a period of 2. You get 0, 2, 0, and then the next number would obviously be 2. So you'd only get a period of 2. You'd only get 2 numbers, 0 and 2. Those are the only 2 you would get, which is not good. And then 5. I want to get to a word. I think one of these is going to cause us to get an infinite. Yeah, there's an infinite loop. So the reason why I wanted to get in this infinite loop is to show you there's a button here, stop the current command, that will stop this thing from executing the infinite loop. So when you're experimenting and you find out that, hey, this little red button is going on and maybe you didn't print it out to the screen, make sure that you understand that that button is there so that you can stop it from going on forever. And a lot of times I like to just restart the kernel whenever I do that. So I'll turn it back to 6. And so let's just make sure that the ones that we think are going to work are going to work. I want to go over to here. I don't know why this thing is not letting me. And put this back. Yeah, I think it was c is equal to 7. Okay, we'll use the same c, that's fine. We'll let m be 100. A equal, what was it, 21? 21. Let's find out what happens here. And it looks like you get a period of 100. What that period means is that I have every number between 0 and 99, right? So you're not going to get 100, but you'll get all the numbers between 0 and 99. So I'm looking for 99 right now. There it is. So the 37th one gave you 99. And what you're trying to do, well, we won't necessarily worry about all that, but what you want is this thing to look random. So there's things that you can do with the C and the A so that you get big numbers and small numbers, and it kind of mixes it up. All right, that's all I got. Hopefully you guys got a little bit out of this particular piece, and we'll see you next time.